Okay, so welcome back for the more speculative part of this mini course. So last time we discussed a bit the Berkeley category of a pair of pants and how homological mirror symmetry works in that example. And so today I want to extend the framework to more general affine hypersurfaces, specifically hypersurfaces in C star to the n. Okay, so, and this is all going to be conjectural because the main examples where we can prove things are for n equals 2, such as the pair of pants. Anyway, so the first thing I need to tell you is there's a general construction of mirrors. And it probably starts all the way back to Hori and Vafa in some way, but the incarnation I will give is joint work with Mohammed Abu Zaid and Ludmil Kizar. So anyway, so what's the construction? So let's say that you have a hypersurface H in C star to the n, and let's say that it's near some tropical degeneration limit. So what I mean by that is it's the zero set of some Laurent polynomial f, which is of the form a finite sum of monomials. Each monomial, there's some constant coefficient that is irrelevant. There's some power of some parameter t, which you should think of as a very small number. And then there's some exponent rho of alpha. So rho is a real valued function on A, satisfying some convexity condition in a certain sense, and a monomial x to the alpha, which means x1 to the alpha 1 dot 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 xn to the alpha n, set this equal to 0, and that defines a hypersurface in C star to the n. Okay, if our goal is going to be to do symplectic geometry on H, so all these details of coefficients don't really matter because all these things are actually symplectomorphic as you vary the coefficients, but this determines a mirror. If you change the weights and things like that, you might get mirrors that change by a flop, and the B model will be the same, but you might not know it right away. Okay? So the mirror is, well, one mirror is a toric Landau-Ginzburg model. So Y is going to be the total space is going to be a toric variety of dimension n plus 1. Maybe I should point out this is of dimension n minus 1. And the simplest way to define it is, let's define it by a moment polytope, which is going to be the set of all, so it's going to be a subset of r to the n plus 1, which is everything that lives over the graph of the tropicalization of f, which by definition is the max for alpha in A of alpha dot xi minus rho of alpha. So my sign conventions are probably different from the official ones. Okay, so this is going to be a polytope in R to the n plus 1. It defines a toric variety with a Kähler class, which we are going to throw away because we are not in that line of business today. And then there's a distinguished toric monomial, which is the monomial with exponents 0, 0, 0, 1 in this description. And we'll take that monomial with a minus sign for good measure, which is also not relevant today. So that's going to be a superpotential. How should I think of this concretely? Well, this is a monomial which vanishes to order 1 on all of this toric variety. And this toric variety, you can think of it very easily by just drawing a tropical H. So a couple of examples to have in mind for today. Well, let's take H to be the pair of pants. So let's define it as 1 plus x1 plus x2 equals 0 in C star squared. Then the tropicalization you get eta has to be bigger than max of 0, xc1, xc2. The way you can picture that is the domains of linearity of this function correspond exactly to the regions delimited by the tropicalization of a pair of pants. So I look at max of 0, xc1, and xc2. And I want to look at what lives above the graph of this thing. And, well, it's skewed, but this is just congruent to a standard octant. So this ends up being y equals c cubed. And the vector 0, 0, 1, which points straight up, pairs, well, has pairing 1 with the normal vectors to each of these facets. So the superpotential will be minus z1, z2, z3, for example, on that. Okay. And so this is the mirror that I alluded to very quickly at the end of last time for the pair of pants, which is a more symmetric one than, so I can think of that as a stabilization of the smaller mirror we were looking at, which was z1, z2 equals 0 inside affine space with coordinates z1, z2. Okay. All right, and you can repeat this with higher dimensional pants as well if you want. So pants in any dimension. It's called the n-1 dimensional pants. Plus x1 plus xn equals 0 inside c star to the n. You can repeat the process, and you'll find that the mirror that you get in this way is c to the n plus 1 with superpotential given by minus the product of the coordinates. Okay. So, all right, and another example that will be useful, just to ground ourselves. Going back to dimension 1, if I look at the variety x1 plus x2 plus, now here's a t finally appearing over x1, x2 plus 1 equals 0 inside c star squared. So that, I think, is a free punctured torus.
You probably said this in the space down.
Yes.
What is the meaning of stabilization now?
In the sense of Orlov's Knorer periodicity. Okay, so up to a completion issue. So maybe I should finish my statements, and then I'll come back to this. Okay, so let me finish my list of examples, then I'll go back to the statement, and then we'll. What happened?
Mom is having trouble with us.
Good luck. Okay. So if you run the calculation on that one, you'll find the tropicalization looks something like this. This is where you'll have max of 1 minus xc1 minus xc2, 0, xc1, and xc2. And I hope I have the right. No, minus 1 minus because of minus. Okay. And then we're okay. And so this guy, now when you look at the stuff that lives above this graph and you think about it, this is going to be the total space of O of minus 3 over P2. Okay, so these are my favorite examples for today. So the statement of homological mirror symmetry in this case is that the Wrapped-Foucault category of H should be equivalent to dB sing of y comma w, the triangulated category of singularities, which you can think of in terms of matrix factorizations, if you prefer. But the definition that I want to focus on for right now says you look at the derived category of coherent sheaves on the singular fiber of this superpotential, which is just, let's call Z is W inverse of 0. And because of what our potential is, this is the union of the toric strata in Y. Okay? And then you quotient by the subcategory of perfect complexes. Okay? So in an example like the pair of pants, you're supposed to think of, so the statement is the Wrapped-Fourier category of a pair of pants should be equivalent to, you look at coherent sheaves on the central fiber, which is Z1, Z2, Z3 equals 0 in C cubed, mod perfect complexes, which are generated by just the structure sheaf. Okay. Now, so Orloff's periodicity statement, which does not quite apply as stated in this case, says if you have a space which is a product. Okay, so maybe I should put that on the sideboard. So Orloff has a statement which says the following thing. Let's say you have a variety which is of a form y is some other, y prime times affine space. And let's say that your superpotential, let's call the coordinate here z. And let's say that the superpotential is z times some function f. F is in O of y prime. There's a more general version which I think is not relevant for today. So we'll just state it this way. Then dB sync of y comma w is equivalent to dB co of f inverse of 0 inside y prime. Okay, so the assumption I believe in your theorem is that you want actually that this should be smooth. And in the case that we're looking at here, it's very clearly not smooth. You can think of this as indeed, you take z1, z2 times z3. You forget then you set z3 equal to 0, and you look at the 0 set of z1, z2, which is this singular curve in affine space. And when you apply, the problem is that actually you get, instead, you should be looking at the formal neighborhood of z3 equals 0 inside this, I think, something like that. Paul scolded me for being imprecise about this. And I'm sure Dima will be ready to scold me soon as well. Okay, but up to some sloppiness, you can think of these two as being similar. The more correct statement is this one by default tends to only have a z mod 2 grading, and then it actually turns out to have many z gradings. But of course, if you look at it z gradedly, there's fewer objects than if you forget the gradings and only ask about z mod 2 graded things. And if you look at this version here, dB co of this has a z grading naturally. And if you choose this z grading, then the objects of dB sing which are compatible with this z grading will match. But this is not the whole story. Okay. Yes?
Silly question, but so in the pair of pants example, your H doesn't have any T in it.
That's right. I don't need any T. I could put some T if you want, but it's rigid. There's nothing to deform. The basic reason is, it's already its own tropical limit. I could put a T if you want. All this does is it's going to shift this by some translation amount. It will not affect the outcome. Pair of pants is a rigid. Basically, one way of saying it is it's a rigid hypersurface. Right? This one, I want to have a T because if I don't put a T, then the tropicalization will collapse the zero section, which would give me a stacky mirror, which would be perfectly okay for most people, but I'm kind of a wimp when it comes to singular spaces. Okay, so I should think in here, the T, or rather what exponent of T I choose, will match the Kähler parameter of this mirror. Of course, since I'm doing symplectic geometry here and algebraic geometry here, this is irrelevant, but it's kind of good for my peace of mind. Okay? Sean looks worried. That's just your usual. Yes. Okay. It's when you stop looking worried that I should worry.
You should just not.
Okay. All right. So this is the statement of homological mirror symmetry, and well, so far this is proved for, let's see. So the pair of pants, this is basically the thing I discussed on Wednesday. This is proved more generally for all hypersurfaces in C star squared, so the case of curves, and this is Heatherley's thesis. I mean, there are other proofs, but the proof that's most directly interesting here is one in Heather's thesis, which basically uses this tropical picture to say, oh, my hypersurface in C star squared comes naturally with a pair of pants decomposition. And this pair of pants decomposition matches exactly the covering of a mirror by affine charts. So if you do this example, you see this elliptic curve wants to come split into 3 pairs of pants, and the mirror has 3 affine charts. And basically, you can match on the nose a restriction diagram for Wrap-Foucault categories along this pair of pants decomposition to the diagram you get when you take the check cover of a mirror by the standard affine charts. So basically, Heather uses, checks this explicitly by constructing nice models of the Wrap-Foucault category here, and concludes that this holds for n equals 2. So for higher pants, there is work by David Nadler, which establishes this. Well, sorry, that's maybe too many question marks. Well, that's mostly my incomprehension rather than something else, maybe. Anyway, so David Nadler has a definition of a candidate replacement of a Wrap-Foucault category in terms of wrapped microlocal sheaves. And for wrapped microlocal sheaves, you can calculate the category of wrapped microlocal sheaves for the higher dimensional pair of pants and check that it matches with a mirror. So then there's a question is, do wrapped microlocal sheaves correspond to the ordinary Wrap-Foucault category? And I understand that Genatra Pardon-Shende will shed a lot of light on this and tell us that the answer is actually yes. In the meantime, I don't quite know what to think. I will tell you also in a bit how I'm going to complete this picture. There's a reason why there's a gap here. In principle, you could have a scheme to compute the Wrap-Foucault category of a higher dimensional pair of pants using conventional symplectic geometry methods that should lead there, but doesn't yet. Okay? And then you could hope to use Heather's techniques in higher dimensions to get to the general case, but that's a different story. Anyway, so the parts that are done so far in the language of actual Foucault categories are just very low dimensional. Okay. So instead, what I want to do today is speculate on what else fits in this picture. Okay? And maybe the most natural question you may have is, well, this is a quotient category, and quotient categories are weird, and can I think of, well, after all, this is, by definition, a quotient of dB co of z. There's a natural functor from here to here, which is quotienting by perf. Does this have a meaning on that side? Okay? So maybe I should call that fantasy or something like that. And I can probably call it a conjecture. Well, I can call it a conjecture. There's no harm in doing that. Which is that this corresponds to the wrapped Foucault category of a complement of H in C star to the n. Okay, so I need to tell you, well, I need to do several things. One is maybe convince you that this is not completely insane, and in particular, I should try to construct a functor from here to here. Okay, and so that's the main theme for today. So we'll add yet another layer to this because it's so much fun that the more functors, the more fun or something. But okay. So let's talk a bit about what this is about. And yes?
What is the label structure supposed to be on C star to the n minus H?
Well, so part of the answer is, well, that's going to be up to you. But the naive thought I have is C star to the n is a Liouville manifold, and H is a hypersurface inverse. So I could probably take something which is just, say you can even think of a Stein structure, which is, if I have to be naive, I would say take the standard plurisubharmonic function on C star to the n, and add a term which is, I don't know if it's log norm f squared or whether it's like, anyway, something that blows up where f goes to 0. Okay? Another way of saying it, which is kind of,
You take one copy of C and then take x times H equals 1.
I don't know what x times h.
You can add
Yes, it's an affine variety. Yes, it's an affine variety. And maybe indeed what I should have said is, one reason, that's kind of spoiling things, but anyway, too bad. Okay, I'm giving my own spoilers. So so you can think of C star to the n minus h is actually a hypersurface in C star to the n plus 1. I think that's maybe what you meant. So I didn't understand what the x times, I think it's exactly, yeah, okay, it's exactly that. It's exactly that. It's the hypersurface defined by f of x1, xn times, plus inside C star to the n plus 1. Right? Because I can solve for xn plus 1, but xn plus 1 is not allowed to be 0. So by just projecting to the first n coordinates, I'll see that this is the complement. And so I can use the Liouville structure that you would think of for this as a hypersurface in.
No, that's just equal to, you mean the times equals 1. That's just, you could just solve for xn plus 1. That's just.
But you can solve for it, but it's not allowed to be 0.
Oh, sorry, I couldn't see that far over.
Okay?
So how does this relate to the other?
Well, how does this relate to the other? That's a good question. So let's do that for the pairs of pants, for example. Okay. Well, or maybe I should just try in general. So if I look at the tropicalization of this one, so let's call that maybe f tilde. Tropicalization of f tilde is going to be the max of xn plus 1, comma, and then phi of xi1, xn. Which means that it's just impossible to draw. So what you should imagine is, I don't know what you should imagine. Well, here's a baby case, okay? If I try to stabilize basically pairs of pants stabilize to each other. That's probably the simplest way to say it. So the statement is the y tilde that I get out of this is going to be a1 times the y that was mirror to h. And the superpotential on that, let's call this guy zn plus 1 out of, do I have that right? Or do I have it wrong? I think that's correct, but see, that's the problem. You guys are pushing me to things I haven't prepared. Anyway, so I think this is correct. And the superpotential will be something that vanishes to order 1 on all of the toric strata, which means it's just the n plus 1 times the potential for h. Okay? And so if you take again this general stabilization principle, ignoring issues of smoothness, you see that dB sing of y tilde w, I'm going to say relates to, out of caution, dB co of w inverse of 0. Okay? So if you believe in this row here, you should believe in the top row as well.
You're
Up to,
telling
yes.
us that the second row is a stabilization.
Exactly. The second row is a stabilization of the first row, in fact. But what's interesting is that it also comes with a natural functor, just because this one is a quotient of that one. All right. So okay. So the question that I want to briefly address is how one might go about building such a functor. Okay. So the answer is, well, what is C star n to the n minus h? The answer is it sits inside, it naturally projects to C star just by taking the function f. Okay? So f as a Laurent polynomial determines a map from C star to the n to C, which may have different properties depending on what you do. Let's do the example of a pair of pants maybe for now. So if I do the example of a pair of pants, let's say I do c star squared minus 1 plus x1 plus x2 equals 0, and I want to project that by 1 plus x1 plus x2, then
So
yes?
You're telling us how to construct this rho.
Yeah, yes, exactly.
To the fiber.
Yes. Yes. So rho is a restriction to the fiber. Okay. So if I do the example, say, of a pair of pants, just so I can draw a picture, c star squared is c squared with the coordinate axis removed. And when I project the coordinate axis down to the sum of the coordinates, it looks like a couple of diagonal lines like that. Okay, but then, of course, I'm also going to remove what used to be h, which was the 0 set of my function f. Okay, so now if I have, so the statement is, if I have a Lagrangian in this, okay, for example, this kind of Lagrangian here, part of the real locus which lives over this, or I can take, other stuff, then I want to get a Lagrangian in H. How do I do that? Well, the answer is I want to restrict to a neighborhood of H and ask what exactly does this look like as it approaches H. Now, approaching H, because we're doing wrapped-Floer homology, each time you get towards here, really, you should imagine that you're going to be perturbing by a Hamiltonian that pushes things around and around and around H. But a key feature is, after all, we're in a situation that's topologically trivial, so there's no monodromy around H. Okay? And that's key to why this has a chance of being defined. So now, going back to this, the statement first is there's a neighborhood of H in there that looks like a punctured disk times H. Okay, so
In the situation you have, like, all the fibers look like H, so why don't you just restrict to a different fiber?
they don't all look like H. The fiber over 0 doesn't look like H.
Not that one.
Ah. So why don't I restrict to another fiber? Well, because the definition of the Wrapp-Foucault category says I have properly embedded Lagrangians. They're going to miss most of the fibers. Okay? And this one has been singled out as being a legal place for Lagrangians to end at.
So there's no monodromy around 0 because it's just a smooth fiber that you remove.
Yes, exactly. I just removed a smooth fiber. There may be singularities elsewhere. Maybe another picture to have in mind is the case of, instead, x1 plus x2 plus t over x1, x2 plus 1. So that one is known to experts because the map from C star squared to C given by this is the mirror to CP2. So it's well known to be a Lefschetz fibration with 3 critical values. The generic fiber looks like a 3 punctured elliptic curve. And what we do is we delete a generic smooth fiber of this. Okay, so delete that one, and you get the complement. So now we have, here again we have some Lagrangians. For example, you could take the thimbles, and instead of sending your Lefschetz thimbles to plus infinity as usual, you could send them towards the puncture instead, and you'd get something which approaches this fiber as the vanishing cycle. Okay, so anyway, there's funny things you could attempt with these. So now the statement is either way, because this is a smooth fiber in a part of the fibration where nothing happens, the neighborhood of it, so the neighborhood of H in the complement can be arranged to be, there's a Liouville subdomain, which looks like basically a punctured disk times H, where this coordinate is just given by the projection to F. Okay? So now the nice thing about Wrapp-Foucault categories is that they have natural restriction maps. Whoa, L for norm of curvature. Okay, so there's a restriction functor defined by Abu-Zaid and Seidel, which is why it's called the Viterbo restriction functor. Well, Viterbo is the closed string analog from the wrapped Fourier category of C star to the n minus h to the wrapped category of, well, let's say punctured disk times h. And punctured disk means really its completion, which is a cylinder times h. So now there's a question of how do you go back down to here to the wrapped category of h. Okay? And there I don't have actually a very good answer, so Paul is going to laugh at me. So here's the slightly wrong. Well, I don't know. So the slightly wrong answer is the following. You should think of, after all, this is a product, mirror symmetry for products is supposed to be what you think. So this is a product of C star with H. And the kinds of Lagrangians we're interested in, they come in kind of radially, or they might twist after a while. But they will be mirror to things that correspond to bundles. They're going to be locally free in the C star direction. And they're going to have whatever they have in the H direction. So what you want to do to restrict to H is take the stalk at a generic point of C star. Okay? Yes?
Yeah, I think all you need to say is that your Lagrangians will be ones that lift to the universal cover, so there's nothing that's like a circle around it.
Yes.
Then those will be Gn equivariant. Right? So that gives you an action of Gn.
And so that tells me that all the points are the same.
And the Gm equivariant is exactly W of H.
That is true. Well, if I wanted to allow more exotic gradings, then I could have Lagrangians that go around, and then I would want to discard them.
Or you
really
want to, well, those ones you can't.
No, those ones you cannot see in dBco of Z, so that's probably not. Anyway.
Yes.
But yeah.
So if you do Gm equivalently, there's
Okay.
no choice of point.
Okay. So stalk at, anyway, I'm going to say stalk at generic point, and Paul points out really the point, Okay. Yes, so you could observe that, if you master equivalent structures, the Lagrangians we get here will have a GM equivalent.
There's no mastering because it's a GM action that's topological.
Yes.
All you need to say is, for every object I choose, okay. The only problem is you need to choose a lift to the universal cover, so there I have to think for a second what I think about to do. But then you just use intersection points that are topologically distinguished,
Mm-hmm.
and then
Yeah.
you get the category for free.
Okay.
The GM.
But I think what this ends up saying is if you chose any circle, the answer would be the same at all of them, pretty much. That's essentially it. Yeah. Yeah. Okay. So anyway, so this, the way I was going to describe this is that it's an adjoint functor to taking the product with S1, with a circle inside the disk. So if I have a functor from the wrapped category of H to the wrapped category of its product, which is just take a Lagrangian to its product with some circle in here, and this has an adjoint functor which is basically test against the generic circle. And yeah, so instead of taking generic, then Paul is saying maybe I should take the exact circle in here and use the
There's a Lagrangian correspondence.
Yes, there's a Lagrangian correspondence, but I still don't quite know how to make them work between wrapped categories in full generality. Yes. Okay. Anyway, so what it does concretely is, anyway, you have a Lagrangian that comes in like that, and you want to know what is it that's coming in when I look in the H factor. Okay. At that level of detail, it's easy. Okay. So now you might ask, what do I know that's not going to be seen by this functor, right? Because you might ask, well, I'm supposed to be killing perf. So can I think of what kinds of things would correspond to perf? Yes?
So, like you were saying before, the stock at the generic point is the end of that.
No. Yes, that's the stalk at the generic. That's if I try to look at intersection with a generic fiber. I'm interested not with a fiber, but with a generic circle that goes around.
So the stock at the generic point is the mirror.
Yes, sorry. It's a stalk at the generic point of a mirror, which means take a random circle in here and intersect with that circle. Okay? Yeah. That's actually much more satisfactory than my other thought was actually you could probably try to restrict to something that's not quite fully wrapped but has a stop here, and that one has a distinguished point, which is the origin, and then you have a stalk at the origin, which might be even closer to the truth, but I think we'll never be able to actually tell the difference because of, yeah. Okay. Anyway. Okay, so now, question you may ask is what kind of under this restriction functor? Well, the answer is obviously Lagrangians in here which don't go to this fiber. How do we build things like that? Well, the answer is think of the thing here as a superpotential and take Lagrangians which instead of going to here, go to there. That's essentially the answer. Okay? So, okay. So let's say this differently again. There's something else called the Fourier category or Fourier-sidal category, but I know Paul doesn't like having the S in the notation, of C star to the n equipped with the function f. Okay, so I can treat f as a superpotential for a Landau-Ginzburg model on C star to the n. So now there's several ways to think about that. Okay. Let's draw the pictures based on the mirror of CP2 because they're less mind-bending than for the pair of pants. We'll get back to the pair of pants in a moment. So you have 3 critical points. And you have, so this category is generated by Lefschetz thimbles, things that look like this. Okay? Sorry. Anyway, I can't really draw them very well. Anyway, so this maps, there's a functor from this to the wrapped category of C star to the n, which would be interesting, but it's not quite what we want to do. Okay, that one would correspond to you forget the superpotential and you start wrapping in the base a lot. And that's good, but once you've done that, you can't go back to deleting H. So instead, first thing I can do is delete a fiber that's chosen to be kind of well out of the way. Okay, so adjust the constant coefficient if you need to, so that H, which is f inverse of 0, lives out of the way of all this stuff. Okay? And then, so there's an intermediate thing, which would be the Fourier-sidal category of this punctured thing. This still contains this one as a full subcategory with the same morphisms, because these guys don't know about this puncture. It would contain extra objects which go to this end or which pass around this puncture. Let's not worry about them for now.
In the language of stops, where would you put the stop?
Here. But I'm going to delete that stop anyway, because I want to go.
But when you say, I mean, I thought you would have put it like there or something.
What do you mean?
Because you don't want those to pass.
Oh, sorry. It's at minus, it's on the other side. But I'm going to immediately delete the stop anyway, because, okay, so first thing I do is I puncture and I delete the stop. Or a way that's more amenable to thinking about Zach's technology. So Zach Selvin says you can glue partially wrapped Fourier categories along stops. So you can think of this as, well, this Landau-Ginzburg model lives over C, but there's a stop here. And then you glue, so this is, in Zach Selvin's perspective, this is, you take this Landau-Ginzburg model and you glue to it a copy. So one of them is C star to the n, comma f, with the other piece is C star times h, with a stop on this side. So again, that's the same as putting a superpotential. So this is a coordinate f, so using f as well. Sorry, calling it f is probably bad, so let's call that, I don't know, S and S. Okay?
The map is projection to C star.
Yes, the map is projection to C star. Okay. So there's now a story about how this behaves, but the basic observation is now you have an embedding, sorry, you have a map, you have a natural functor from here to here. This functor is no longer fully faithful because as we forgot this stop, now these guys will get wrapped around infinity. Okay? But these things definitely don't go to this puncture, which means that this lands in the kernel of this projection. Okay? Now, there's other functors from this to that, sorry, to here, which do not land in the kernel. Okay? Because instead of making my left set symbols go to the right, I could have made them go to the left and plopped them down into that missing fiber. So there's another functor, which I will, let's see, need some color. Let's try a red functor maybe, which instead take these Lagrangians and, well, maybe I'm just going to draw them that way and not worry about sidedness. Takes basically, so you could argue, is this still the category of f, or is that the category of minus f because I flipped sides, and I'm not going to take sides on that. The two are equivalent, okay? So anyway, so now you have another functor, and that one definitely does not land in the kernel of rho, okay? So again, well, and there's more actually because you could do other things, but these are the two natural ones to think about. Okay, so the question is, what do they mean under mirror symmetry? So here's the candidate answer. First thing I need to tell you is what is this category? Okay, so you know the answer in the case of the example with P2, right? You know that the category of C star squared with Z1 plus Z2 plus 1 over Z1 Z2 is meant to be mirror to dBco of P2. So in general, there's a distinguished component Z0 inside Z, which remember was the zero set of a potential inside Y. What is this component? It's the component of a constant term. So now I should probably point out.
Meaning that the one.
Okay, so let's go back to our examples, which I've all erased. The example of CP2, I had f equals, x1 plus x2 plus t over x1, x2 plus 1. Okay? And so and now when I tropicalized, I got this thing that was max of 0, xc1, xc2, and minus 1 minus xc1 minus xc2. And the domains of linearity of this thing gave me a picture of the toric divisors of y. So now I want to take the toric divisor corresponding to the constant.
This makes some assumption on your function.
Yes, this makes the assumption that there was a constant coefficient in my function.
Where the other ones are bigger.
No, the other ones just are different monomials with non-zero exponents.
The origin is maybe.
This is sort of the compact piece. Is that always the case? Or?
Well, in general, I could have something that has so many terms that it's like a something of genus 50, and then there's a lot of compact components.
Or you're still just taking one little thing?
So let's do another example.
The origin has to be in the interior of
No.
the polygon?
Oh no, it doesn't have to. The whole thing is.
For the origin, right?
Sorry?
The constant term is the one for the origin.
No, it's the one for the constant term here. The origin can be anywhere it wants. This is all translation invariant. It's a moment polytope. So what it means, okay, let's talk about this.
Before the translating involved using t.
Oh, the constant term could involve a t. Yes, I could put a. Okay.
A constant just corresponds to the points to the origin in z to the n. No?
Yes. Oh, yes. Sorry. In the list of weights, the z to the n. Yes. Yes. It corresponded to the origin in the z to the n's of monomial exponents. That's right. Okay. Sorry. That's.
But if you don't care if it's in the boundary of the convex hull of the things.
No. In fact, the next example I was going to give was again going back to the pants. For the pair of pants, my favorite choice was 0, xc1, xc2, and then this is the one I'm looking at. Okay?
Yeah, but
So it depends on the choice of normalization of f, and that's a key point. Okay, so let's go back a little bit for a moment. We said h is defined by some equation, f. Well, h doesn't know if I'm taking f or if I'm taking x1 times f or x to the, So there's a choice of normalization. I will choose a normalization so that there is a constant term in here. Now, when I project using f, I've used basically the framing induced by my choice of normalization to explain what I mean by trivializing the normal bundle. And in particular, the rest of the topology here will depend very much on that choice of what normalization I used. Okay? So I didn't do the homework, but I suspect that if you take the thing for CP2 and you multiply everything by x to the 10, you will get a very different story. Okay? So I'm assuming there's a constant term, and I'm making a choice of normalization, and for each choice of normalization, there's a different pair of these red and white functors. Okay? So now, the statement is similarly, my choice of normalization singled out one of the components of the toric divisor inside Y. Yes?
I mean, here we're torus, some function. I thought sort of the general thing would be, you know, that would correspond to a compactification of the dual torus. So we'd always just get some toric variety.
Well, this one, okay, so now let's talk a bit more about Mohammed's thesis. Okay? So let's say that F was actually bigger, so that the tropicalization had, sorry, this is probably a bit nonsense. Let's do instead my favorite genus 2 curve with a bunch of punctures. Okay, there's something like this that you can do. Okay? And now there's two bounded components as well as several unbounded components. Now, what Mohammed's thesis tells us is, so you can think of in several ways of this Lano-Ginzburg model in this category. So one way is you can try to do, critical points, Lefschetz thimbles, and then you get lost quickly. Or you can do what Mohammed does in his thesis, which is to say, look at admissible Lagrangians for this superpotential from the perspective of a log map. And specifically, look at the component of 1 and look at Lagrangian sections over the component of 1 with boundary in a fiber of F. And then he shows that this portion of the Foucault-Seidel category is equivalent. So if you just look at Lagrangian sections, this part of the Foucault-Seidel category is equivalent to line bundles on the mirror toric variety. Okay? And of course, in a setting like this, if you instead looked at that component, well, actually they look the same, so that's probably a problem. But anyway, you'd get coherent sheaves on that toric variety instead out of the guys who live here. But these guys are not admissible for the same choice of F because it's a different choice of framing. See, the category of Lagrangians that Mohammed would look at inside this hole or versus in that one are not admissible for the same F. The Fs have been normalized differently. So this is exactly this business of picking which term will be the constant term. Okay? And if you look at all the Lefschetz thimbles, so if you take the original definition of this category in terms of all the critical points of F, you have the things you want which live in here, and you have a bunch of sporadic things which are not directly relevant to your life. So what I mean by that is actually the piece that living over, what should I say, log inverse of the correct component. Okay, sorry, this is a horrible notation. Okay, but I mean, so by this I mean in the sense of, well, the piece living over where F is less than 1.
Sorry. So a piece of that is the mirror to there.
So a piece of that should be the mirror exactly to this particular toric variety, Z0. Okay? So this category, we know by Abu Zaid's thesis, is equivalent to dB co of Z0. Okay? So let's go back to this picture up there. Yeah? Just a second. I'm just going to complete my diagram again. Okay. Sorry, so what I mean by that is, maybe I should say, well, norm F is less than 1. Okay?
Usually, kind of F involves things going out to F being very large.
Yes, but so the statement I want to make is this has critical points that I care about, and this may have other critical points that I don't care about.
So
okay, so it's the thimbles that
only the critical value
use, yes. Z0 further? We'll talk about, well, I think the answer is this is maybe one more level in this whole jungle of functors. I'm going to have a little piece of that goes to codimension 2, but it's kind of in the other, it's going to be in the other direction out of necessity. I'm sure there are things, basically this picture, the more you look at it, the more functors you see, and this could keep going on forever. It's this kind of thing. Well, sorry, yes? So the double arrow means that I have at least 2 functors in there, right? I have 2 preferred functors, one which takes, if you want, Lefschetz thimbles and sends them towards the missing fiber, and the other one that takes them away from the missing fiber. Okay, so maybe I should actually draw one in white and one in red to match with. Okay? Yes, well, at least one of them.
Remind me again, just Z0 is just P2, right?
So in the case, in that example, Z0 is just P2. If I use the usual normalization, if I normalize differently, say multiply all this by x1 inverse, then Z0 will be this component, which will be instead O of minus 3 over P1. I get to choose which one. Okay, but by default, I'm going to think of P2, yes. Okay. So
Z, sorry, I forgot what the Z.
Z is the union of all the toric divisors.
Oh, okay.
It's W inverse of 0 in the ambient thing. It's the union of all the toric divisors.
So one thing is just
Yes, exactly. And that's the red one. Yes, that's the red one. Exactly. So let's check that this makes sense. Paul has seen it, but so the claim is the red one is the push forward by inclusion. So let's think about it. Well, first of all, the red ones, okay, so again, red one means you take Lefschetz thimbles and you have them going to the missing fiber. Okay? So when you compose the red one with restriction to the missing fiber,
Restriction, right?
sorry?
It's bigger. Z0 is the P2 and Z is the bunch of boundaries of P2, right?
Z0 is P2 and Z is the boundaries in the total space of the anticanonical bundle. Okay? So Z0 is a component in Z. Okay?
So another factor is the pullback.
Yes, exactly. Okay, so let's see, people, yes, exactly. So it's pullback and restriction. So it's pullback to, so I'm going to write it for P2 and examples like that because I don't quite know the general answer.
pullback means collapsing the other components.
Yeah.
Yes, so it's a yes, it's a yes. So there's a projection from this thing to, this component. At least in the examples I've looked at. Sorry, I don't have a good general, but yes. So it's a pullback to the total space to Y, and restrict to Z. Okay, so let's do that by example because it's easier to think about. So if I do this thing of P2 and I'm singling out the 0 section P2 inside the total space of the okay, pullback.
Pullback to Y.
Yes. So again, I have P2,
Okay. Well. Okay.
which is the 0 section inside the total space of O of minus 3. I can just pull back by this projection. So if I have a sheaf on P2, I pull back to get a sheaf on the total space, and then I restrict to the union of the toric divisors.
All you really need is to have Z contract to Z0. You're going to restrict to Z anyway.
No, it can be written as a pullback on the the composition of this morphism.
Right. That's right.
Yeah. Okay. So yes. So I can just do it on yes.
Just collapse Z to Z0.
Yes. Okay. That's true. Yeah. Okay. So you could just yeah. Yeah. But saying it this way makes it clear. Maybe it was clear even before. But it was clearer in my mind, at least, that this would automatically land in perf. This lands in perf because Y is smooth, and so I know that pulling back, Z0, if Z0 is smooth, then everything here can be expressed in terms of vector bundles, which pull back to vector bundles on Y with restrictions.
Any kind of pullback.
Oh, any kind of pullback.
Of perfect complexes. Perfect.
Okay, so if you're Dima, you know right away that,
But
yes.
we didn't start with a perfect complex, right?
Well, we did because Z0 is smooth.
Smooth, right.
Okay, Z0 is smooth.
Okay.
Yes, okay, so pull back to, yes. Okay, so we could just say pull back by, there's a natural projection from Z to Z0 which collapses all the other components.
Does that mean that some intersecting points?
Sorry, say again?
Can you imagine some configuration where another component of Z intersects Z0 in two different
No, they don't.
No, because it's a toric diagram. See, it's governed by the tropicalization. So there's always a polyhedral decomposition of Rn, and the diagram is a union of toric varieties described by these things.
So you collaborate in the direction. Basically, because those are the constants,
okay. So you-
there's
so
like
you-
a GM action that moves everything down.
Okay, so we are using.
Yes, so we're using we're using the global toric structure to get there.
And you're using the fact that this particular stratum is the constant.
Yes, yes, to single out which subgroup I'm acting on. Yeah, sorry. Okay, so just now for people who didn't. So this one which goes to pullback lands in perf, which means it will die in here, and that corresponds, that mimics the behavior of the thimbles going this way, which manifestly don't hit the fiber I'm removing and restricting to. Meanwhile, the other one, the red one, which I claimed is inclusion, so that one is kind of interesting. You take thimbles going to here, and now when you compose with restriction to that fiber, you could forget that you had actually ever wrapped at that fiber. This is just the same as you have a Landau-Ginzburg model, you restrict to the fiber. What does that one do? Go back to the world of toric mirror symmetry. You know that restriction to the fiber in this Landau-Ginzburg model that's a toric mirror corresponds exactly to restriction to the toric boundary. So the composition of the red one sorry, that's not going to be that either.
Can you
Yes.
what is the name of that statement? Where do I find the proof of that statement?
Which statement?
The restriction to the fiber is restriction to the toric boundary.
It's implicit in Abu Zaid's thesis, I would say. It's stated as a speculation in the last section of my 2007 paper, and it's kind of well known to experts. It's probably also part of, it's all over Paul's papers. It's all over Paul's papers. It's the observation that, thimbles, when you restrict to the boundary, you get the vanishing cycles, and the relation between morphisms in the category of a Lefschetz fibration versus morphisms in the category of a fiber exactly matches what you get when you restrict to the anti-canonical divisor. Okay, so think of the example of P2. If I take the red thing, which is inclusion of the zero section, and now I include the zero section into this singular configuration, and then I pass to dB thing, which means I kill perf. Well, it turns out this is again a case that's stabilized. I mean, it's twisted because it's O of -3 instead of product with C, but you can still think of it as this will reduce to the zero set of, well, basically it will reduce, So what I want to say is, in the case of P2, for example, this contains something which looks like dB of this triangle configuration, which is just the codimension 2 strata. Okay? And the composition you can think of now as being just restriction from this. So this is the toric boundary of Z0. So the composition of the red functor and the quotient functor and inverting some sort of stabilization statement is just restricting from Z0 to its toric boundary in a way that mimics restriction to the fiber of a Landau-Ginzburg model is restriction to the boundary divisor. Okay. Is that enough speculations for? Okay, so these are the main, speculative functors I wanted to introduce. And now I wanted to spend the last 10 minutes telling you how you might use this to compute the Bragg-Fourier category of higher dimensional pairs of pants.
So okay. You don't know statements like the Chi category of the fiber is coherent using the toric boundary, or you do know that?
We know that.
Okay.
Do we? Well, we kind of do in all cases where the fiber and the toric boundary are understood. So this has mostly been done in dimension 2. In dimension 2, it's apparent. You have a restriction to a punctured elliptic curve, and it's obviously.
I believe you put dimension 2.
Yeah. Nick would probably know. Actually, wait, isn't that more or less what you're working on, Nick? No. So the question is, take Mohammed's picture for mirror symmetry for line bundles on a toric variety as things that live over unmissable Lagrangians with boundary in the fiber. Now you can restrict to a category of a fiber. Do we know that this matches with homological mirror symmetry between the fiber, between the fiber of a Landau-Ginzburg model and the toric divisor? And so.
Okay, so we need. There's one additional datum which is needed, which is the Mohammed's category comes with a natural transformation.
That's
from the
right.
functor to the identity.
Yes.
And you need to know that that is the section of the anticanonical that cuts out the toric boundary.
Yes, but that's not written, but that's not how.
There's further obstructions, but I think they all vanish. They're all negative, hopefully. Now, what we know a priori, just from the topology, is that this natural transformation must be toric. Okay.
But you can compute it explicitly,
yes,
I think, from Mohammed's
I
picture.
mean, at this point here, God could hate you, and it could be the toric divisor in some multiplicities. But you just need to compute how it acts on one object, like O or something. And so I believe this can be done. Is it in the literature? No. So
No,
basically, you need to take, Lefschetz. I mean, there's the paper, right, for categories of Lefschetz variations. One, it makes exactly this statement. You need to adapt it to Mohammed's situation, which is technically set up a bit differently. And you need this computation, and then you'll be done.
Okay, that's Okay, so now the next thing I wanted to do is tell you quickly about pairs of pants, and let's think about. So there's two ways to do that. I can try to go from the zero-dimensional pair of pants to the one-dimensional pair of pants, which has the advantage that I can prove everything. But you'll get completely lost. I mean, apart from Paul, who gave this wonderful, when I was a postdoc, I sat through this wonderful course by Paul where he explained a lot of stuff about zero-dimensional Lefschetz fibrations. And we spent a lot of time on gradings of Lagrangian zero spheres, which actually turned out to be very useful for later. But it's the only dimension where a sphere is a union of two tori, and that's very disturbing. Okay, but okay. So anyway, maybe I'll run the two in parallel. Okay. So maybe one thing I want you to remember very briefly is that when I calculated the Wrap category of a one-dimensional pair of pants, I said something like this. I want to think of it as C star minus a point, which I chose to be -1, which now I can reveal was actually the zero-dimensional pair of pants as a hypersurface in C star. Okay? And then I said, well, we pick a trivialization of a tangent bundle, which is the expected one at these things and non-trivial at that one. And then we have three things. This one will correspond to O on the mirror, and this one was O sub A for one component, and this one was O sub B for the other component of the mirror. Okay? Sorry, for the mirror, which was xy equals 0, is A union B. And so this is actually an instance of this whole setup for the zero-dimensional pair of pants. Because what you want to say is exactly you had the wrapped category of C star minus a point going to the wrapped category of the point, which would be just restricting to this puncture. Okay? And this corresponded to looking at the mirror of a point as a hypersurface in C star. You can run this argument. Okay, -1 is the zero set of x plus 1 equals 0, which tells you want to look at max of 0, C, which singles out C squared with the potential minus Z1, Z2. So I should probably, well, I guess I call them XY now, but maybe I should change that to Z1, Z2. Okay. So if I run this, I actually have something that tells me this corresponds to dbco of xy equals 0. And this one corresponded to db sing of xy equals 0, an isolated singularity. And you can check that everything matches. Namely, these two guys, which run into the puncture, O sub A and O sub B, give rise to the generator of db sing. Whereas, well, this guy O lands in the kernel. Okay? Baby example, not very useful yet. But let's call these Lagrangians also L12, L1 and L2 for future use. Sorry, debasing of. Oh, that's sorry. That's what I meant. That's the same thing. Okay, debasing. You can express it either in terms of superpotential or in terms of the zero fiber. That's anyway notation thing. Okay, maybe I should say yeah, debasing of minus xy. Okay. All right. So now, if you do this instead for the one-dimension higher pair of pants, then you can start having some fun. Because, sorry, let me send all my functors up there. And of course, if you know, so basically what this is going to look like is some sort of half-baked inductive scheme for understanding Foucault categories of pairs of pants. So the observation is, we said, the n-dimensional pair of pants you can think of as C star to the n minus x, which is exactly the n minus 1 dimensional pair of pants. Okay. So if I use my usual picture, I'm going to want to think of, so let's do the case n equals 2. I will project C star squared containing the two-dimensional pair of pants linearly by x1 plus x2 to the complex plane, and I will delete, well, I can put plus 1 if you want, and then I delete the zero fiber. Okay, so I think of a two-dimensional pair of pants as the complement of these three lines in C squared projecting down here. So the two interesting things happen here, where there's the origin, and here the missing fiber. Okay, so the typical fiber of this thing is a pair of pants. This fiber here, however, two of the punctures degenerate together. Okay, and you should think of that as this is the interesting accident in the Landau-Ginzburg model C star squared, comma, x1 plus x2 plus 1, which is a mirror to C squared. So the closest you have to a Lefschetz thimble is this guy here, which is, let's call L0. L0 in general will be R plus to the n in this setting.
So the vanishing cycle joins two of the ends.
Exactly, exactly. So what it does on my typical pair of pants is it joins two punctures, the two punctures that have merged here. Okay? Yes? Yes, but I'm going to have to upgrade my notation at some point. Sorry. I'm going to overload the notation because I'm going to restart with a new set of notations. Okay, and at some point it might restrict to, yes, this, yes, so L12 equals L0, and maybe here I should say equals L12 dot 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 n. Okay, if it helps. Which in this case would be 1, 2, 3. Sorry, L12 n plus 1. That's my notation. Okay. So now, what other things do I have in here? Okay. So the ones I like, well, I could take L0 to this side instead, which is the other way of embedding dB of C squared. Okay, so I've said, okay, so maybe I should make a dictionary as I go. Right? So I'm supposed to think that this corresponds to C to the n plus 1 with, no, C to the n plus 2 with minus, what do I want to say? No, sorry, it's a complement. So it's the hypersurface z1 dot 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 zn plus 1 equals 0 inside n plus 1. Right? Yes. No, it's going to be easier if I just use n equals 2. Well, whatever. Okay, now that I've written it correctly. Okay. And so this one should correspond to O. Okay. And you can ask, well, does it work? And actually, you can compute by hand the self-wrapped Floer cohomology of L0. How? Well, observe that this came from C star to the n. And the Liouville structure is kind of essentially the same as long as you don't get near this thing. and this Lagrangian doesn't get near the missing fiber. So you can just compute, and you don't need to know about the missing fiber. Okay? What you need to know, however, is when you compute the ring structure, if you were in C star to the n, you would get Laurent polynomials in n variables. Okay?
Why does the fact that the Lagrangian doesn't go near that fiber mean that this is going to go near that fiber?
Let's keep it in if you want, but basically it will not matter.
Maximum principle.
Yeah, okay, maximum principle.
But they don't.
They don't.
Yeah, doesn't matter. I mean, example, okay, let's redo the example here. When I computed the wrap-Floer homology of this guy, I said I'm going to wrap here, I'm going to wrap here, and I never needed to worry about wrapping here. Okay? Now, holomorphic curves get modified. Okay, so when I computed the endomorphisms in the cylinder, I said there's these variables which look like C bracket x to the plus minus 1.
I'm sorry, I said the wrong thing.
Yeah, but that's okay.
There's no differential anywhere.
There's no differential anywhere.
Sorry, that's what I should have said. There's no
And it's
differential
all in degree
anywhere.
0 for the standard grading from C star to the n. Okay? So this instead came as generated by, I could think of it as, this thing. And I said when I puncture, I lose all the triangles that involved both powers of x and y. So this became xy equals 0. And so here the same thing happens is, you have polynomials in n plus 1 variables, and if you are doing the calculation corresponding to basically the Reb orbits along this coordinate axis, let's call that z. Gosh, it's all messed up. My picture is all messed up. Let's call that z2, let's call that z1, and the one at infinity would be z3. And the relation in r plus to the, in C star to the n would be that the product of these is equal to 1. But now you can see that exactly those products which involve holomorphic curves that pass through the thing that you've deleted are exactly the ones that involve all of these variables, so that the new relation becomes product equals 0, which is kind of a good, confirmation that you're getting what you want. Okay, so that is actually an easy calculation in there. Now, the next Lagrangians you might worry about are, well, what if I take this thimble-ish thing and instead I send it to the missing fiber? So this one I will call Ln plus 1, but for simplicity here I will call it L3. Okay, so Ln plus 1, well, actually in general I will think of Li as corresponding to the structure sheaf of a component Zi equals 0. Okay? And in general, similarly, I will denote multi-indices as being, skyscraper sheaves of divisors which are unions of some hyperplanes. And so then the correct labeling of this is L2 free, L1 free, L2, L1 2, and L1. So the claim is actually I can now look at all the components of the real locus and split this into 7, it's split into 7 components. This is way more than you need to generate, but these are good enough. And you can match these 7 components explicitly to the structure sheaves of unions of hyperplanes. And the basic structure is that the ones you see here to the left. So now we can talk again about, this was a pair of pants, the missing fiber. There's an inclusion functor, which is kind of, goes in the opposite direction from the one I discussed before, which takes an object of a wrapped Fourier category of this pair of pants and includes it over an arc that goes from this missing fiber to infinity in that direction. Okay, so L12 is I take an arc that connected 2 punctures of my pair of pants and I push it here. Okay, and what is now the notation on this side of the diagram should be reminiscent of what we had here. Okay, so the statement, all the stuff that you do by taking Lagrangians here and including them here, is exactly the inclusion by taking the things where the last coordinate does not appear. Okay, so this inclusion here I should think of as I had a union of things in the hypersurface in Cn given by z1.zn equals 0, and I take the product of that with the z1 coordinate axis, and that gives me all but one of the hyperplanes in here. And the missing hyperplane is the one that sits here, or everything is that one. So now you can go talk to Zach, who tells you that you expect in general that the category out of gluing principles is generated by these things and either this one or that one, depending on what you choose. And then you can calculate based on that. You can calculate how these guys behave as modules over the previous ones. More importantly, you can use this embedding functor to get a lot of exact triangles. You know that these guys fit into exact triangles here. That tells you automatically these three fit into an exact triangle, actually 2 exact triangles. And then you can permute this picture using the fact that there's more symmetries than what you see. And out of that, you see that basically you can calculate all of the Hom spaces in terms of as modules. And you can check that whenever you have 3 of these things aligned like that, along a straight line through a vertex, they fit into exact triangles. And that, I believe, should determine the category, but I don't know for sure. Okay, the end.